1. What specific problem does conditional language policy, CLP, aim to solve in the context of multi-objective reinforcement learning for language models? How does it improve upon the limitations of standard single-objective fine-tuning and existing multi-objective approaches?
Conditional language policy, CLP, aims to address the limitations of single-objective fine-tuning, SOFT, and existing multi-objective approaches by enabling a language model, LM, to generate outputs based on varying reward weightings without the need for retraining. SOFT is constrained by fixed reward functions and KL weightings, making it incapable of adapting to different objectives post-training. In contrast, CLP employs multitask training and parameter space conditioning, allowing it to learn a conditional policy that can maximize a weighted combination of multiple rewards at inference time. This results in improved steerability and output quality, as CLP can effectively trade off between conflicting objectives, outperforming zero-shot methods like rewarded soups, RS, and prompt-based approaches. The systematic experiments demonstrate that CLP consistently Pareto dominates existing methods while maintaining robust performance across various conditions.
2. Can you break down the algorithmic steps of the CLP method? Please illustrate the process from sampling the prompt and reward weightings to the final policy optimization. What are the key components involved in each step?
The conditional language policy, CLP algorithm consists of three main steps during each training round. First, the algorithm samples a prompt, x_t, and reward and KL weightings, w_t, alpha_t, sim, q_text cal line, sample prompt weights. This step ensures that a diverse set of weightings is utilized to enhance the model's performance across various objectives. Second, CLP conditions on the sampled weightings, alpha_t, w_t, and generates outputs, y_t, sim, pi_t, x_t, alpha_t, w_t, line, compute condition generations, allowing the model to produce responses tailored to the specified objectives. Finally, the algorithm computes the conditioned objective, line, compute objective, and updates the CLP parameters using policy gradient methods, line, update phi parameters, which maximizes the defined multi-objective fine-tuning objective. Key components in this process include the sampling mechanism for prompts and weightings, the conditioning on these parameters to generate outputs, and the optimization step that employs standard policy gradient techniques to refine the model's performance.
3. What empirical results did the experiments yield regarding the performance and steerability of CLP compared to baselines such as rewarded soups and prompt-based approaches? Can you provide specific metrics or observations that highlight these results?
The experiments demonstrated that the conditional language policy, CLP, consistently outperformed baselines like rewarded soups, RS, and prompt-based approaches in both performance and steerability. Specifically, CLP and its instances, full CLP and ATTN CLP, exhibited Pareto dominance over RS, particularly in the 3-reward setting, where full CLP outperformed RS at intermediate weightings. Automated evaluations showed that full CLP achieved an 11.6% improvement in win rates compared to the multitask trained prompting baseline and A4. 9% improvement over RS, indicating superior generation quality and steerability. Additionally, ATTN CLP maintained a favorable trade-off between parameter efficiency and performance, achieving competitive results with only 20% of the memory overhead compared to full CLP. Overall, CLP's robust performance across various experimental conditions highlights its effectiveness in generating high-quality, steerable outputs compared to existing methods.
4. How does the parameter conditioning mechanism work in CLP? Specifically, describe how the weights from different policy networks are combined for generating conditioned outputs and the implications of this method on steerability and memory efficiency.
The parameter conditioning mechanism in the conditional language policy, CLP framework involves maintaining multiple sets of condition parameters indexed by a specific set of LM parameters, denoted as SCAL, and one set of unconditioned parameters. To generate conditioned outputs, CLP linearly combines the M conditioning parameters with the specified reward weightings, W, and then merges this result with the reference parameters, theta_ref scal, weighted by a function, f_text SF mix alpha. This results in a full set of parameters, theta_alpha W, that can be used for generating outputs based on the desired reward and KL weightings. This method enhances steerability by allowing the model to adaptively respond to various reward configurations without retraining, thus enabling a smoother transition across different objectives. Additionally, the parameter count of CLP is designed to be memory efficient, scaling with the size of the conditioning set, scal, and the number of reward functions, M, which allows for effective trade-offs between model expressiveness and resource usage. Overall, this approach ensures that CLP can produce high-quality outputs while maintaining a manageable memory footprint.
5. What are some limitations or drawbacks of the CLP framework as highlighted in the paper? In which scenarios might CLP underperform compared to other methods, and what factors contribute to these limitations?
The CLP framework, while robust, has some limitations as highlighted in the paper. One significant drawback is that it may underperform in scenarios where the reward weightings are not well represented in the training data, particularly for intermediate weightings that the model has not encountered during training. This is evident in the findings that zero-shot approaches like rewarded soups, RS, can be suboptimal for these unseen weightings, as they rely on linear mode connectivity, which may not generalize well. Additionally, while CLP is designed to be more steerable than prompt-based methods, it can still be sensitive to the choice of parameters indexed by scal, which affects both steerability and memory usage. Lastly, the paper notes that CLP's performance may degrade in cases where the optimal policies for individual rewards are not aligned, necessitating multitask training to achieve Pareto optimal behavior.
6. Based on the findings from the paper, what future directions can you propose for enhancing conditional language policies, especially in terms of addressing the identified limitations or extending their applicability?
Future directions for enhancing conditional language policies, CLP, could focus on improving steerability and performance in zero-shot scenarios, as identified in the paper. One approach could involve further refining the parameter conditioning mechanism to enhance the model's adaptability to unseen reward weightings, potentially by integrating more sophisticated multitask training techniques that can better capture the nuances of diverse human preferences. Additionally, exploring hybrid models that combine the strengths of both parameter-based and prompt-based methods could lead to improved performance, particularly in contexts where prompt sensitivity is a concern. Another avenue could be the development of more robust automated evaluation metrics that can better assess the quality and steerability of generated outputs across a wider range of tasks and datasets. Finally, expanding the CLP framework to incorporate additional reward functions or multimodal inputs could enhance its applicability in real-world applications, such as conversational agents or summarization tasks, thereby broadening its utility in various domains.